I'd like to again welcome you to SimScale webinar on optimizing ventilation in power plants with computational fluid dynamics. My name is Pavel Sosnovsky. I will have the pleasure of being your host for the next couple of minutes, maybe tens of minutes. Let's jump in. A short word about myself. I'm working as a customer success engineer here at SimScale, and I specialize in computational fluid dynamics with a particular look at evaporation and condensation phenomena. At the same time, I have a very wide range of interests, and some of you might have already met me while working with other projects or asking with the support team. So, without further ado, let's go and see what is it we're going to talk about today. We'll start with a traditional discussion about the benefits of using simulations and a very short introduction to SimScale. After that, a quick walkthrough. We'll go to the topic of the day, that is the ways to optimize your design of a power plant on an example of a power plant for the industrial project. We'll have a live demonstration followed by a results summary and a short discussion, and we'll close up our meeting with a Q&A. Let's start with the benefits of using simulations. Why should we actually bother? In very many cases, especially when we're dealing with civil engineering and big projects, it is not possible to directly investigate or predict the behavior of the system before it is constructed. Of course, we have a lot of references. We've been doing it for pretty much the whole time while our civilization has been up here, and we have a good understanding of how things should be done. At the same time, this is not an optimal approach, and still there is place for improvement. Computational fluid dynamics and in general computer-aided engineering allows you to get an understanding of what is going on within your system with a great level of accuracy without having to build it and be potentially doomed to fail or be required to make significant modifications to your design or improvements or to fix errors that were not provided while defining or working with the references as the base. So we could be doing this to validate HVAC systems, predict wind loads, check the thermal comfort, improve the energy efficiency or control of air quality within the room, and many, many more applications. Improve pedestrian comfort, make sure that your building is not undergoing significant loads. Now, what is so different about SimScale? What does it make it? What makes it so special? Well, first of all, you will be able to accelerate your design process by using the platform that is running completely in the cloud. This means that you have a product which has all-in-one capabilities with the computational aided engineering projects range and applications ranging from structural mechanics to fluid dynamics and thermodynamics. No need to get an additional package when you want to simulate a structural load after calculating a flow around such an object. The use is fast and easy. We make sure that the workflows are streamlined and user-friendly. We have a very good, and I'm pretty proud to be a part of the support team who do their best to make sure that you get your answers to the problems that you face while working with the simulations. The solution, of course, is cost efficient. We come at a fraction of the price of the other competitors on the market, providing you access to a secure tool with significant capabilities of supercomputers running in the cloud. And last but not least, we have a great community. We are all here as a part of this simulation community who want to learn about using computer-aided engineering, and many of these engineers are willing to share their knowledge and expertise with others to enable them to have a starting point on their own projects to make the world a better place. What kind of applications can we run with SimScale? You just name it. since we're dealing with all this, we're covering basically all simulation types, applications are endless, from industries such as electronics, energy, marine, machinery, aerospace, automotive. Simply give us a call, ask how are things going, and we will be very happy to talk with you about your application and make sure to find the matching approach with the tool that we have to make your designs better. Okay. We went through this short introductions. I promise that it will be short because we're all interested to jump into the topic of the day, that is optimizing the ventilation of power plants and looking at the ventilation in generator rooms using computational fluid dynamics. What is it that we're trying to optimize within a simulation like this? Well, the first thing is that we will be looking at the energy efficiency of such an industrial application block. The cooling engine rooms require energy, and they will be generating a significant amount of energy. The performance of such an engine will depend on the temperature outside and might be subject to misoperation or bad behavior while operation when the temperatures are increasing or above the expected levels. To cool the room, we will need a significant amount of air to ventilate within the generator room. So we will have to have fans that provide fresh air, and this requires energy. The temperature should be kept as low as possible to allow operating at the optimal conditions. And we'll need to have a balance between the temperature that is present in the room and the amount of energy we are using to provide optimal operational conditions. Of course, the more energy we use, the more expensive it is to operate such a facility. And having the possibility to optimize such behavior is a great benefit to any engineer. Let's take a look at the general application that we'll be looking at. In principle, such a power generator room will consist of multiple engines set in a continuous fashion, one next to the other. The great benefit of using models like this is that we can simplify the whole room and assume symmetries. So that will mimic the presence of a set of generators while reducing the computational cost. In this case, we will assume that we have two rows of engines adjoined with the symmetry that is on the big wall, the tallest wall on the right, and also that there are multiple engines standing next to each other, so that the front wall and the back wall of this geometry will also facilitate a symmetry condition. We'll have multiple engines. At the same time, even though we're making this assumption, it is a good approximation, especially for situations where we have multiple engines standing next to each other. Then other important components are the engine, the generator, and the exhaust that will be generating heat and introducing it into our system. Let's take a look at the air ventilation parts that will be simulated in the design 1 type. We'll have the outlet that is positioned on the top. This is where we'll try to take out the air. The inlet duct that is located at the left side on this vertical wall will be assumed to have a certain angled grating or louvers that direct the flow at the 45-degree angle towards the engine. We will model this using the specific boundary condition type that I will show you during the live presentation. Next, there is the radiator, which takes away the heat, and there is a certain part that is the intake, which will be sucking air inside into the radiator object. So this is the radiator intake. And on top of that, we have the maintenance platform and some scaffoldings that allow us to access the engine. This is just to visualize obstacles or significant obstacles that will affect the behavior of the flow. Notice that the geometry has been cleaned up of small details. We don't have any rivets, we don't have any bolts sticking in, or, for example, textures put on the maintenance platform. The geometry represents only the most crucial elements required to make the simulation work and to visualize the behavior of the system, while removing features that are not significantly important to the behavior of the flow itself. Let's take a look. So this is a visualization of the whole system that we're trying to work with. And as I mentioned, we're using symmetries to limit the amount of computational power required to calculate the behavior of such a facility. The design parameters that we'll be looking at consist of the inlet positions, how do we want to work with them, the ventilation setup, how much flow rate are we going to introduce into the room, and the places where we locate the inlets and outlets. The room, we will be looking and modeling, trying to find out what is the average temperature inside the whole room, and then, very importantly, what is the temperature close to the engines themselves. We will locate, this is what we will call throughout the presentation the engine height average temperature. Imagine that we have a plane that is just above the engine, and we'll take the average temperature of all the air that is below this virtual plane. That will be what is happening next to the engine itself. Then the operation of any engine and the operation of the radiator is significantly impacted by the temperature that enters into the radiator. We would like it to be as low as possible, so we'll be monitoring this as it goes. And finally, the decision can be taken based on the flow rate parameters. Our objective is to find the best balance between the efficiency of the performance for the room, so lowest temperature in the room, while keeping the lowest possible volume flow rate and maintaining the temperature of the room, or the temperature in the vicinity of the engine, that is not higher than 10 degrees above the ambient temperature. Okay, to visualize that, we will use a cost function that will be weighting behavior of two parameters. The first of one, which will be the flow rate, and the second one will be the temperature. Both of them will be assumed to have the same weighting, so we put as much interest into maintaining the optimum temperature as well as the volume flow rate itself. We'll get back to this cost function and discuss it a little later when making the decision which of our designs works best. Now, this table gives us an overview of different scenarios for design 1. Please ignore the last few lines because they already have the results present. We will be jumping back to this slide and to this data to investigate the actual behavior of the simulations as we go. First, let's focus on the type of flow rates we're going to work with. We'll start with a very low flow rate, that is 15 cubic meters per second. We'll be increasing this to 18.5, 23.5, 28.5, and 33.5 cubic meters per second. The inlet area will stay the same since this is a part of the geometry we're working on. The second scenario will actually have a different inlet configuration. While having the normal inlet velocities, we'll be able to calculate the actual velocity that is entering into the room. And then with the results, we can calculate the room average temperatures, the engine height temperatures, and so on and so forth. But this is to come. Right now, I would like to take you to SimScale platform and show you the features themselves and how did we actually perform this analysis. All right, I took the liberty to already open the project and load some things. Please keep in mind that right now I'm working live online with SimScale platform. So all this is being operated as we go. We have the geometries load here. Let me load design 1. There we are. You can visualize the object. We can hide some of the walls and take a closer look at what is it that we're modeling. SimScale allows you to upload different types of CAD, ranging from the one that we like the best, the STEP, the industry standard, to most of the available, the big names for CAD development. And also we allow you to get access to your geometries in the cloud that work with Onshape, our partner. I'll not do that, but in this case you can also get your geometries out there. In principle, we leave CAD operations to the experts, and you need to prepare your CAD before you upload it to SimScale. But after that, all the simulation steps needed to get your results and take engineering decisions are done online. Let's take a look at the first mesh that we prepared. The great power of using SimScale is that you have the choice of how do you want your meshing operations to work. You can always take the automated route, and this is what I'll do in just a second. So let's create a new mesh on design number 1 as an example. Let's add an operation. So you can either start with an automatic approach where all you have to do is select how fine you want your mesh to be. If you're interested in using the latest developments of SimScale team, you can use our beta preview hex dominant mesher, which is automatically updated with the latest features we developed. Of course, it's not as stable as the other released features, but you are always working with the cutting-edge technology that we develop here with the team. At the same time, if you want to have full control over your simulation setup and your meshing setup, you get the possibility to do that. All you do is go for a parametric approach where you get access to all these nice settings with multiple types of refinements that can be done in order to prepare the mesh that matches your expectations and matches your needs. Some would say, I get a little overwhelmed with all these possibilities. Where can I learn about this? Well, that's where you have these webinars like this. We have quite a lot of series of training webinars that discuss in details how to approach these meshings, which are available on our YouTube channel. You can also use the help section with the documentation, the learning videos, or you can approach us directly with a chat, asking questions. We'll try to answer them as soon as possible. But please give us some slack. If it takes a minute or two, of course, there's a lot of people. But there's one more place that I would highly encourage you to check. That is the SimScale forum, because with this tool, not only do you get access to SimScale team, but to hundreds of engaged engineers who are willing to share their knowledge, who are willing to share their expertise and help you get your simulations running. Okay, but I'm getting a little off topic. Let's get back to our meshing tool and our mesh for design number 1 and investigate what is it that we decided to choose in order to obtain this mesh. For this particular case, we used the Hexnomen parametric, where we manually decided to set up the refinements around the features, around adding additional layers for boundary layer refinements, and if it loads a little more, oh yes, it's loading a lot of setup. There are a few thousand faces that need to be selected. That's why it takes a little while. And then surface refinements around the engines. I'll simply reload this so we don't have to wait until it selects a few thousand steps. A very good thing to do whenever you're working with SimScale is to try not to use internet too much, the way that I'm doing right now, streaming this this interesting webinar, of course, the more bandwidth you take, the longer it takes for the things to be streamed directly to your screen. And this only regards the visualizations. Every calculation that you run on the platform is done on the cloud. Once I would click Start in the meshing operation, I can shut down my web browser, go home, come back next day, or travel to China or Brazil for a business meeting and get back to work while sitting in an airport. Anywhere in the world where you have internet access, you can get simulations working for you. Okay, we finished working on the mesh, and I jumped through it as if it was a standard simple thing. Basically, you will use 60 to 80% of your time mastering and making sure that the mesh is working as good as possible. But after you have the mesh ready, you are able to jump to the next step on the top menu bar, that is the Simulation Designer, where we will be actually setting up the analysis to replicate the engineering process that you want to work with. I'll go to Design 1, Scenario 1. We have, as you can see, several of them. And this is where, again, the power of SimScale shines. You can have any number of these simulations running at the same time, and all of them may be running on multi-core machines in the cloud. These simulations were running on 96 cores, and as you can see here, we have around 10 scenarios, so 10 simulations, all running on a supercomputer. Imagine if we were to try running this on a single machine. Even if this is a powerful desktop that you have with, let's say, 16 cores, you would spend weeks, or at least a week or 2 weeks, just simulating it. All this done in the cloud with one click of a button. Oh, maybe two. Okay, let's take a look at the setup itself. We have the mesh selected, and we decided to go with convective heat transfer simulation. SimScale gives you immediately access to multiple simulation types, ranging from incompressible flow simulations to structural mechanics or thermomechanical simulations. All this immediately available when you get the platform working. We work with different turbulence models. We allow you to choose either steady state or transient simulations, and you can go with additional approximations to speed up your process, be it that it is a little simpler and it is actually applicable. Okay, let's jump in. All you have to do whenever setting up a simulation on SimScale is to, first of all, create your template, and I'll maybe show you how to do it. Let's right-click, create a simulation, convective heat transfer, click Save. And once I select the simulation type I want to work with, once it saves, what will happen is that you will get this empty template of your project ready to be filled. All you have to do right now is go from top to the bottom, assigning every leaf for this simulation tree, entering it step by step, and making sure that your properties match the analysis that you want to run. Very straightforward, very simple, and always the same, working the same way. So let's take a look at what was set for this case. The reason I'm clicking on the model is that this is where you decide the direction of gravity. I cannot stress how many times I forgot to set this up, and I was running a simulation on an International Space Station with zero gravity. So make sure that this is selected. After that, we decide to go and choose the material. There's quite a lot of properties that you can tweak when deciding on the type of flow you want to analyze. At the same time, if you are not sure or you would like to get a quick access, we have a material library that gives you instant fill for some of the basic materials available. We jump to set up some initial conditions and go to the boundaries. We start with defining the outlet, which will be set on the top face. Notice a very peculiar thing. The outlet face in the design that I was showing a little earlier was very close to the room itself. And now we have this extended domain. This is a modeling technique that allows you to stabilize your system. Actually, all the flow that is happening in this chimney, let's call it like this, we consider to be trash. This is not important. It's only there to stabilize the analysis and will be disregarded. If I was interested at what is happening next to the outlet, while processing the data, I would cut it in the middle and I would investigate only that plane. Anything that goes above the line that I'm showing with my mouse right now is disregarded and not important at all. Now, I promised to tell you how we decide to have a directional flow. And in this case, we want to have our inlet of the air that is marked with the blue section here to go at 45 degrees towards the engine. And the way you do it is extremely simple. All you have to do is decide what is the direction and the magnitude of the vector is pointing. So I select this plate and I say, insert a fixed velocity flow that goes at 1.66 meters per second downwards and negative 1.66 meters per second, which roughly corresponds, well, I think it would be 2 meters per second. All you have to do is do a little bit of trigonometry to calculate the magnitude of this flow. So this is how you set up directional flow entering the room. Let's take a look at the radiator. This is a custom boundary condition type where we decide that we want to have flow that goes at negative 3 meters per second on this particular face. What it will mean is that, well, the flow goes in the left direction, so it's being sucked out of the engine room and being taken away from the device. Then we have several symmetry faces. This is how we decide that we have multiple engines in the row, and the boundary condition is extremely simple. All I have to do is set symmetry on the planes of symmetry. Next, many of the surfaces that we have here will have no effect on the thermal behavior of the system. These are the adiabatic walls, like scaffoldings, or we actually consider the building to be perfectly insulated, or at least not to pose a significant change in the temperature. This is where we select all these faces and assign a zero gradient temperature boundary condition. Of course, this system needs heat, and we'll be introducing it through a heat flux boundary condition with a certain flux density coming from the engine and the generator itself. We're almost ready to set up our simulation to run. Very often I get a question, how do I treat the numerics? There are so many very complex options to be chosen here, and I'm a little lost. The answer to that is take a reference. What you have available with SimScale is a huge library of public projects, some of them very complex, some of them really industry relevant. You find a project that looks something like your project and you mimic the settings. At the same time, the default values we're providing you are applicable to most of the applications that you have. So in general, you don't have to touch it very often. Next, we go to the simulation control, where we'll decide on how long do we want to run our simulation. In this case, I'll be running it for 1000 iterations, saving only the last step. For steady state analysis, I'm only interested in the best approximation of the flow. And I want to run this project on 96 core machines. So I choose the most powerful machine available. For smaller projects, you can also go with less cores. Last but not least, I can immediately monitor some of the parameters of the flow, such as averages on the inlet face, the average temperature at the outlet. I could put probe points to visualize the value of temperature or other flow parameters somewhere in the room itself. So you can choose these probe locations and see their behavior as the simulation runs. While it is going, you can monitor the progress in the viewer. So it would be, let's say, set to running 53%. You can see the behavior of the flow residuals, and once the job is done, you will receive a message saying you're ready to post-process your results. Now, there are two ways to approach visualizing the data that you acquire. You can either download your results to do the post-processing offline on your powerful computer, or before you do that, you can jump to the post-processor and visualize data online without downloading them. Now, this will take a brief second because we have a big case over here, but I will load one of the post-processing state that we prepared earlier so that we can visualize the flow and take a look at the system itself. Or you know what? Since I know that there will be more questions later, let's leave it to load slowly by itself. We'll just take a look at the screenshot I took of this post-processing state, and if there are more questions, we'll get back to this during the Q&A session, because we have a bit of slides coming in. So this simulation ran for around 2.5 hours on 96 cores, and I would say it weighs around 1 gigabyte of data, which could be downloaded and processed. So if you want to know how your flow looks like without having to download everything and unpack it and processing it, you simply go to the cloud and visualize the state. But again, we're dealing with big data sets. That's why it takes time. Of course, you don't have to have a very powerful machine to do that. We wouldn't require you to do that. Actually, what will be happening here after the post-processor loads is that we will be streaming the images, the interactive visualization images, to your computer. So the only thing you do is running some basic graphic operations, while all the rendering, all the calculations, and 3D visualization is running on our clusters online. This is actually the place where we'll need most of the bandwidth while post-processing. Oh, there we go. You see, it took a while to prepare all these elements, but we get to the time frame 0. So this is the initial conditions. And if I jump to the last frame, we'll be able to visualize the whole flow with the glyph vectors and with the slices themselves. Okay, let's give it a moment and see as it goes. While it loads, I can also show you the behavior of the probe points. So for example, I could be monitoring the behavior of the temperature at the outlet while it is being calculated. So the outlet data, all these steps are available while the simulation loads. To visualize the flow field, you will have to wait for the simulation to finish. So this is only available after we get the final data stage, while the probe points and all this setup is available while everything runs, and you can make sure that the simulation is converged and ready to go. There we go. So here we have a flow visualization with the magnitude of velocity showing the inlet that is blowing air downwards into the engine, a big recirculation vortex that we'll discuss in a moment, and the outlet that takes away the flow. Okay. That would wrap up the live demonstration. Let's talk a little bit about the results. So, having the data downloaded, we can start processing it and calculate, for example, the average temperature in the room by integrating all the temperature. We could define the height, the radiator inlet temperature, also visualize it, and to normalize the flow rates that we are actually inputting into the system. With this information, so the normalized flow rate and the normalized room temperature, we can calculate the cost function that decides which scenario behaves in an optimal way. And if we plot this on a graph that is shown over here, you will notice several things. Number one, we have a pretty high temperature room, and as expected, the lower the flow rate, the higher the temperature. So definitely increasing the flow rate will improve our behavior. At the same time, the second graph, that is the dotted line, which indicates the engine height average temperature. So what is the average temperature below this, around the engine itself? We can see that it is all above the red line, which indicates the maximum temperature we allowed. It seems that design 1 does not perform, and it should be ruled out since one of the design conditions we had is not matched. On top of that, the dashed line indicates the temperature entering the radiator, which we can see is significantly higher than the average temperature in the room. That would say, well, our radiator will not be working efficiently, and we definitely should think about an improvement of the design. Furthermore, if we take a slice and visualize the flow direction and the temperature around features, we can notice that, well, there is a big jet coming from the inlet, but this jet drives a significant vortex that develops in the cavity of the room. This vortex limits the possibility for hot air to be taken away from the engine. It is actually blowing the hot air downwards to the floor while it recirculates. And, well, it is taken away, but at the same time it is in a way pushed into the radiator so that it increases the temperature that is present around the operating devices. A choice, so let's take a little closer look at the rendering of the high temperature values. This tries to show the temperature above 303 Kelvin, which was the limit that we put ourselves. So all the room is basically around the engine is above the required temperature, and hot air is being pushed downwards around the engine. It's not the way that we want to take it out towards the inlet. There is a plume that comes on the left side, on the far side, like next to above the generator, and is being taken away by the big vortex, but on the other hand, most of the air is taken into the radiator and decreases the efficiency of the device itself. We can see a little more by visualizing the streamlines around the device. So again, a big vortex, the air is being recirculated around the radiator and it's being sucked into the device. Now, how can we improve this? Well, let's imagine that we will add additional ventilation system that runs below the floor of our room, and some of the tiles that are within the system will be the inlets. This is where we'll be introducing fresh air. At the same time, the window that was open on the right top side will be closed. So right now it is considered to be a wall. This table summarizes the performance of the second scenario. with the temperatures and data, but let's visualize all these nice numbers on a good plot. And with this said, while putting it on the graph, we see, first of all, the temperature, the average temperature in the room seems to be much bigger, especially for low flow rates. This is expected since we have a better mixing of the temperature. At the same time, the temperature in the vicinity of the engine is much lower. And actually only at the lowest flow rate we are not matching the design criterion we set ourselves. So every flow rate above 18.5 meters per second will allow us to have temperature of the engine only 10 degrees higher than the ambient, which is very good for performance. And of course the temperature that is entering the radiator is also lowered significantly because the heat is taken away, is moving towards the inlet instead of being recirculated and pushed into it. Let's take a look at some graphs. First of all, we will notice that the air itself is moving towards the outlet and the recirculation vortex is basically not present at all. We have there is some air that is being directly moving towards the outlet. The cold air on the very left side of the image, there's a big tile that was the inlet itself, and it's directly going to the outlet. We could optimize this design by moving it somewhere else. So there are further optimizations, and we see that there is quite a lot of hot air gathered in the far end behind the radiator. So some kind of a forced convection that would take it away would be a good choice. At the same time, the engine itself is operating in wetter conditions. So let's take a look at the streamlines. Once more, I will point out that there is this big flux coming from the inlet on the closest to us behind the generator and is pushing air upwards. Now, if we take a look at the cost function, we know that only the design number 2 matched the criterion for the temperature around the engine itself. So we'll be looking at the cost function for this operational condition. And we know that the first flow rate that was given, the 14 or 15 cubic meters per second, it was not matching the criterion. So we look for the minimum, and actually the two operational conditions with 18.5 and 23.5 cubic meters per second would be the optimum choice for operating this plant. And basically the cost function for both of them is more or less the same. And in this case, in order to maximize the performance of the plant, we would choose the lower operating conditions, still knowing that we are matching the criterion for the operation of the plant and having the lowest operation cost for not using energy to push more volume of air into it. Okay. That would close up the whole process for this particular project, or at least a first iteration of optimizing the flow inside the generator plant. After having we could take another round of iterations like this by importing a new CAD with a little modified inlets or outlets, or changing the shape of the geometry. Then using the existing setups as references to quickly set up a mesh and run a simulation, further processing the data and taking another engineering decision. I know that you all are anxious to do it yourself. I highly encourage you to join SimScale if you haven't already, or to work with your projects if you already do. And for the time being, I'll be open to answer any questions that you had during this presentation. So, thank you. And if you have questions, please raise your hands so I know that you're typing right now. I'll wait for you to finish typing. And yeah, please, go ahead. The floor is open. Okay. I see the first question. Is it possible to simulate the temperature inside the engine? Yes, it would be possible. At the same time, you would have to ask yourself a question. Do you really need to know everything that is going on inside the engine while simulating the air around it inside the room? Actually, in this case, I would split the problem in two. On one hand, I would simulate the engine itself to see its thermal behavior, and the second thing would be to run a simulation of the room itself without modeling the engine itself. I would consider it like a black box that gives a certain output of temperature that I calculated with another project. At the same time, if you want to run simulations that consider both solids and fluids and the thermal behavior of a solid, we do have such a feature. It's called conjugated heat transfer, where you actually model the flow of air or water, like a fluid, and the solid objects. This is like one of the examples, the electronics cooling simulation. Okay. Next question. Let me go through. Can I simulate varying temperature at the inlet? Yes, this can be done. Not only can you modify the temperature at the inlet, so let's take a look at the simulation designer again, and the simulation setup. So air vents, there we go. So not only can you set the fixed value, but you can also set functions that vary in time and space. You could, for example, define a profile of velocity that is having a jet that enters from the middle, and then it is zero at the walls. A very nice public project I did some time ago actually does this. You can run simulations that are combined of multiple other simulations. Like use one, calculate the values of the inlet, and then set it up as the second inlet, as an outlet for the other simulation. So it is definitely possible to be done. Okay. Okay, in academic plan we don't have an option to run 96 cores. So what would you suggest in this case? We have maximum limit of 32 cores using academic plan. Yes, this is true. So this is one of the benefits while running a professional plan or becoming a professional user for SimScale. The thing is that most of the simulations, the CFD simulations we're running over here, scale really well with the size of the computers. So it will take you a little more time, or roughly 3 times longer, to make the calculation, but you will pay the same amount of core hours for your operation. Let me just do one thing. Yes, so a rule of thumb I would apply when choosing the amount of cores that you run, that you calculate, is whenever your mesh is bigger than 10 million, I would go with 96, or the maximum number of cores. If your mesh is around 4 million elements, you go with 32. 2 million is good for 16 or 32. For 1 million mesh cell volumes, you go with 8 to 16 cores. And to be honest, I never go below that. So, yes. The next, so I hope this answers your question, and I highly encourage you to, well, get trained in the academia and then either start your own company work, get a professional plan, and, well, earn money while simulating. Okay, which turbulence model should be used depending on various models? This is a very good question, since we have multiple turbulence models available. So let's jump to the project. So if you know that your flow is not subject to turbulence, that is, the Reynolds number is below the threshold for the flow conditions, you would go with a laminar flow. That's pretty obvious. Then most of the time I would encourage you to use K omega SST model, which is in a way became a standard for the industry itself. It tries to take the best approach, or try to take best of both K epsilon model and K omega model, mixing the two and calculating the turbulence properties more or less correctly next to the walls and within the flow where we have shear flows. I actually almost always run with a K omega SST model. Now, when it comes to the LES models, they are available, but they will require you to have a very fine mesh next to the boundaries. So to make sure that that you need to be sure that your mesh is really good to run them, although they will improve the accuracy of the calculation. Okay, waiting for some more questions. How long should be the outlet? You mean, oh, okay, so how long should you, I guess you mean how long should we extend these outlets in comparison to what we have in the design? The answer depends on the amount of recirculation you expect. What you want to make sure is, okay, let me grab a drawing tool. It should be available somewhere here. There we are. So the whole idea is that we are trying to prevent the flow to go back into the domain. Once you have an outlet, and let's say there is like a big recirculation vortex, it might be that some part of the air would try to go back into the flow area from the outlet. This is very undesirable. So you try to set it up as far as necessary to make sure that the air only goes out and it doesn't come back into the domain. In this case, I see that this has been done like 8 to 10 times the thickness of this object. But again, this really depends on what is the flow behavior that you expect in your system. So definitely extending the outlet is important. How fine? It really depends. It might be that your simulation doesn't work because of this kind of backflow that comes from the outlet, and then you need to extend the outlet even further. Okay. All right. So I do not see any more questions. If you have anything else that you would like to ask, please raise your hand. Oh, I see one more hand up. Let's wait for the typing to finish. And in the meantime, I can show you some more post-processing tools. So for example, how did we make this post-processing? Well, first of all, you can use opacity. This is a very nice feature. I'm right now only showing the solid color and adding opacity to the model. So it will be translucent and showing the thing nicely. Yeah. We have a nice slice. And there are more interesting post-processing tools, like let's say that we would like to see where is the temperature that is very high. So I can choose contour. And contour with temperature. Please take your time while typing the questions, but I'm definitely here all the time. We'll be waiting. In the meantime, we'll set up a contour of temperature, a few contours of temperature. To see where we are at. There we are. So each of these surfaces will denote a different temperature level. Let's say that this velocity. Let's color this with velocity. And I guess we'll have to rescale it. Okay, there's another question. What is the role of y plus in this simulation? What values should we look for in this case? Yes, so y plus, the non-dimensional wall distance, defines how good are we resolving the flow next to the wall. For the models that we're using over here, you would try to get your y plus values at any surface that is not moving to be in a range between 30 and 200. This is the target. Of course, if you have several cells that are not matching that, it's okay, but for more, you would have to change it. Oh, I'm really sorry about that. It just started raining. I hope that you don't get too distracted with the rain pounding on the window, but it's a storm outside. Okay, so with y plus, you try to ensure that your flow is actually properly resolved next to the wall, and the values are 30 to 200 if you use wall functions. This is done, let's say here. Once we select one of the boundary conditions, you have the wall function set up for the behavior of velocity. Okay, the next question, where does the radiator discharge hot air? In this particular case, we are assuming that it's just being taken out of the facility, I guess through this opening here. So we are not bothered by it at all. It's just taken away. But at the same time, you're raising a very good question, like what will happen if the hot air enters the radiator? Of course, it will diminish the operation conditions, and the radiator itself will become hotter, which is not being modeled here. But we are, this is why we are modeling the temperature that goes into the radiator. If it is too high, we immediately know that the system will not operate at optimal conditions. And we could set some more restrictions on what is happening within the flow to facilitate for this feature. But in this case, it's just taking it away. Next question. Oh, I'll just go to the question, but I appreciate that you like the presentation. Can you create custom materials? Yes, you can. So in this particular case, we decided to load a material from this rather short material library, but of course, you can change any of these properties over here to facilitate the fluid that you want to simulate. And yeah, so change it to some air 1, make it a little heavier, and change the dynamic viscosity to define a certain mixture that you're trying to analyze, and you're ready to go. The next question is, how do we position the ventilator locations? Well, of course, one thing, you already have some information about this when you're designing the facility. So I would know from the design that was given by an architect or another engineer that says, hey, I want to have the inlets here. That's my idea. And we take this from the experience of the designer himself. And then I would simulate it and say, okay, look, this particular tile that we have here, let me just get the surface with wireframe. So this particular tile blows cold air into the room, but everything is immediately taken out through the outlet. It makes no sense. So let's take it out, let's make it smaller, and put another outlet somewhere here, maybe, in this area. This will be like the next iteration I would do for a problem like this. So the choice of the location is arbitrary. There is one more interesting feature that I didn't mention. You can also create virtual ventilators. So I could create, let me see, what do we have here? Oh, these are just points. Sorry about that. So let's create a new cylinder. And I hope that I will not, yes, this is very good. Z, let's set it up to be 2 meters. It needs to be 4 meters, let's say. Let's say that I would like to simulate a situation where I have a fan that is positioned just above the engines. For any reason, somebody decided that this will be a smart place to put a fan. Or you know what? I'll just make it a little smaller that it makes more sense. So a fan is positioned over here for any reason. All I have to do to facilitate the presence of this fan is add what we call a momentum source. And I will say that the air will be virtually pushed through this disk that I created here. Let me just create it. And it will be from the performance of such a fan, I know that it will be pushing it with 2 meters per second. Would I like to, what happens if I put this fan in a different location? So this is like scenario number 1. Let's put the fan in a different location. Let's move it 1 meter to forward. Scenario number 2. And so on and so forth. And you can run all of them at the same time. So this is how you set ventilators. And when it comes to the boundaries, well, for the boundaries you have to prepare them in CAD. Okay. Another question, can I tell if it is necessary to apply feature refinement in Mesh Creator on geometries, and what is the purpose of this refinement? If we don't apply it, will there be any advance on the simulation? So the feature refinement itself is working around the elements of the CAD. So let's load the design itself really quickly. Notice that the CAD itself not only is composed of solids, but of surfaces and solids, but also you have these edges that are around here. Like every element here, we have multiple edges. A feature refinement will automatically generate a mesh. It will improve the mesh quality around these features, so around the CAD elements here. It is not strictly necessary to use this kind of refinement. You could also get reasonably good behavior if you use surface refinements. For some particular applications, you would go with a feature refinement, for example, to facilitate, to make sure that your tiles are properly represented, you need a feature refinement. But, so yeah, there's a reason. But it's not like a strictly necessary. You can get a very good simulation without dealing with it. Okay. There is one more question, and this will be the last one. If you have more, we'll go. So moreover, what is the Brzezinski approximation? I can direct you right now to the documentation at SimScale, because I would have to give you a lecture on approximating thermal flow simulations. So it basically makes your simulations faster, supposed that the temperature difference in your system is low. So you can have only few degrees of change, of variation in your system, and then it is just calculating it quicker. If you have bigger temperature differences, you should not use the business scale approximation. But some more informations, and for more questions, please, first of all, post them on the forum. There's a lot of people who will be very happy to answer them. Ask us as the support team. We're also trying to do our best to answer them as fast as possible. And of course, get trying with your own work on the platform. We're very happy to have you here. And I hope that you found this presentation informing and well, encouraged you to use numerical simulations as the part of your design process. Again, if you have any questions, go to support@simscale.com, or even better, post on the forum, because there's much more people who can help you. For the time being, thank you very much for taking your time this evening with me, or morning. On behalf of the whole team, once again, thank you, and hope to see you on the platform. Paweł Sosnowski, signing out. Bye-bye.